In this video, we will be starting a new chapter, and in this chapter, we'll be looking at counting principles. So throughout these next video lessons, we'll be learning different counting methods that will allow us to solve complex counting problems that are really applicable to real-life situations. So let's take a look at the first lesson. Alright, so we're going to learn how to count without counting. So many techniques in probability and statistics are based on counting. And in this chapter, you will learn some strategies and shortcuts to count when the numbers are very large. Alright, so let's look at some applications here. Basically, the kind of counting strategies that we'll learn in this chapter will allow us to help solve the applications listed below here. So if we want to look at the number of favorable hands when playing cards or gambling, we can use the counting strategies used in this chapter to help solve these kind of problems. We can also look at applications of the lottery. How many different ways can you do something and possible outcomes? Seating plans, menus, license plates, and passwords. So we'll definitely learn how to find all the different combinations for these applications. And we'll also look at some favorable odds when making a decision, which is directly related to probability. All right. Let's start off with a very basic example. How many different ways can you arrange the three letters A, B, C? Well, there's a few ways to do a problem like this. There are three ways to count. The first thing you could do is you can list out all the possible outcomes and count how many there are. So there's ABC, there's ACB, there's BAC, BCA, CAB, and CBA. Now when you count the different outcomes, we have a total of 6 different outcomes. So that's the first way to count. You can list out all the possible outcomes and count how many there are. Another way where you could figure out the different ways to arrange A, B, and C is by drawing a tree diagram and counting how many different branches there are. So for A, B, C, we have 3 different outcomes. We have A, B, and C. If we start off with A, that means we could have B or C for the second letter. If I pick B, then that means C must be the final letter in the third outcome. And if I have A and if I have C for my next letter, then that means the third letter must be B. And if I draw out similar branches for the letter B, then I'll have A and C. If I pick A, then I must have C. If I pick C, then I must have A, and that will complete all the branches for the letter B. Now, if you start off with letter C, then that means you can have B or A. If you have B, then that means you must have A for your final letter, and if you have A as your second letter, then that means you must have B for your third letter. Now, if you count the different branches, here's 1 branch, here's 2 branches, this is the third branch, this is the 4th branch, this is the 5th branch, and this is the 6th branch. So there are 6 different branches. Now another way where you could find the different outcomes for A, B, and C is to apply the fundamental counting principle, which is denoted FCP. Now we're going to in this lesson we're going to talk about how to apply the fundamental counting principle to word problems. But for this problem here, basically how the fundamental counting principle would work for this problem is that you look at how many choices you have, so A, B, and C. So you have 3 choices for your first letter, and if that first letter, if you use one of the letters, that means you must have 2 choices for the second letter. And since you've used 1 letter here and 1 letter there, that means there's only 1 letter left for the third choice. And what you would do is you would just simply multiply these numbers across, 3 times 2 times 1, which will give you a total of 6 outcomes. So that's the fundamental counting principle. All right, so let's summarize the fundamental counting principle in the next slide. What is the fundamental counting principle? Well, it's the rule of product, and product means you multiply. So if we have X number of ways to do the first task and Y number of ways to do the second task, then there are X times Y ways to do both tasks. If there are several different tasks, then we can have unlimited. We can have as many tasks as there are. So going up to nth tasks. So there are a number of ways to do the first task. So in the first task, maybe there's A ways to do it. There are B number of ways to do the second task. There are C number of ways to do the third task, and so on. Okay. So when we apply the fundamental counting principle, we have to find out how many ways are there to do the first part, how many ways are there to do the second part, how many ways are there to do the third part, and so on. And then we simply just multiply the outcomes all together. So the total number of different ways to do all the tasks together will be A times B times C times D all the way to E, depending on how many outcomes and tasks there are. And this is called the product rule, rule of product. You're simply just multiplying the different outcomes together. All right, let's take a look at a simple example here. How many different course meals can you order at the Salmon House if there are 3 different appetizers, 4 main courses, and 3 different desserts? So here is a sample menu here. And if you look at the appetizers here, we have 3 different appetizers, red, blue, and it looks yellowish green. And for the main dishes, we have 4 different choices: 1, 2, 3, 4. And for desserts, we have 3 different choices: 1, 2, and 3. All right. So how many different 3-course meals can we have? All right. So we could have an appetizer, we could have the main dish, and we could also have a dessert. All right, so we're going to use the fundamental counting principle to count how many different meals are possible. Multiply the number of choices in each category. So once again, for the categories, we have appetizers, mains, and desserts. So for the appetizers, we have 3 different choices. So there's 3 different appetizers. And for the main dishes, we have 4 different course meals. And for desserts, we have 3 choices. So 3 times 4 times 3. This is the AKA the product rule. Like there's A choices for the first part, there's B choices for the second part, and there's C choices for the third part. So this would be 36 different meals. Let's take a look at another example. How many combinations can you make if there are 10 different icings, 16 different ice creams, and 10 different cones? All right, so I guess for this question, we're walking into an ice cream store, and we want to know how many different combinations of an ice cream can we have when we have these different choices. All right, so once again, we want to apply the fundamental counting principle. So we have 10 different icings. We have 16 different ice creams, and we have 10 different cones. So 10 times 16 times 10 will give us approximately 1,600 different combinations. So once again, if I kind of refer this back to the notation that we used from the previous slides, 10 is representing, like, we have A, like this is your A, this would be your B, and this would be your C. And you just simply multiply those numbers across and you'll get 1,600 different combinations. All right, the iPhone has 4 different numerical passwords. What is the total number of different passwords that are possible? All right, so this is an older iPhone model. And if you want to log into your iPhone, sometimes you'll be asked for your password, a 4-digit password. And I want to know what are the total number of different passwords that are possible. Okay, the first method is count all the possible outcomes from the smallest to the largest number. So you could, a possible password choice could be 0000, and the last number that you could have is 9999. And if you, sorry, 4 nines, and if you count all the different possibilities between 0000 and 9999, you'll have approximately 10,000 different number possible, 10,000 different choices or combinations. Now, if we apply the fundamental counting principle, then this is the second method using the fundamental counting principle here. We want to multiply the number of options for each digit. So this is your how many options do you have for part A, part B, part C, and part D. So there are 10 choices from each digit. So if you look at this first slot right here, you can have 10 different choices for the first number. The first number could be 0, it could be 1, it could be 2, it could be 3, all the way up to 9. So you actually have 10 choices for the first slot. And for the second slot, you also have 10 choices. It could be a 0, a 1, a 2, a 3, a 4, all the way up to the number 9. So you have 10 choices for the second slot. And that means you have 10 choices for the third slot, and you would have 10 choices for the last slot. So if you take 10 times 10 times 10 times 10, you would get 10,000 different numbers. All right, let's move on to the next example. All right, so if the first number is not a 0 and the second digit is not odd, then what is the number of possible outcomes? All right, so I guess we have another password situation, a 4-digit password, but this time we have a few restrictions, meaning that the first number cannot be 0, and the second digit here is not odd. Then if we apply those restrictions, then what are the possible number of outcomes that we can have? All right, so let's take a look at the fundamental counting principle one more time. If we look at this first digit, usually we will have 10 choices for the first digit if we're dealing with strictly numbers here. But the first number is not 0. So for the first digit, we can't have a 0 there. So that means how many choices are available for the first slot here? So that means we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means we have 9 choices for the first digit. Now for the second digit, once again, normally we would have 10 options for the second digit if we're talking about numbers strictly. But in this case, the second digit is not odd. So it can't be odd. So it can't be 1. It can't be 3, it can't be 5, it can't be 7, and it can't be 9. So the second digit, the second digit can't be odd. So we can have 0, we could have 2, we could have 4, we could have 6, we could have 8. So we have 5 options for the second digit. And for the third slot and the fourth slot, we don't have any restrictions, so we can have 10 choices here and 10 choices there. All right, so the third digit we can have 10 choices there, and the fourth digit we can have 10 digits as well. So we just have a 10 here and a 10 there, and we simply multiply these numbers across. And when we do 9 times 5 times 10 times 10, then we'll have 4,500 different outcomes. Let's take a look at another password situation. If the last digit must be even and no number can be repeated, then what is the number of possible outcomes? Okay, so the last digit must be even. So the last digit is the fourth digit. So this digit right here must be even. So let's take a look at the possible choices that we could have. So normally we have 10 digits, but the last digit must be even. So once again, it can't be 1, it can't be 3, it can't be 5, it can't be 7, it can't be 9. So if it's even, we have 5 options for the last digit. So it could be 0, it could be 2, it could be 4, it could be 6, it could be 8 for a total of 5 options. All right, and then it says no number can be repeated. Then what is the number of possible outcomes? Okay, let's take a look at this. Now for the first digit, one even number is gone. So we know for the last digit we've used an even number already. So this even number could have been a 0, it could have been a 2, it could have been a 4, it could have been a 6, or it could have been an 8. The point is we've used one even number already. So what that means is if we use the number 2 for the last number, that means this 2 is no longer available for the first choice. So one even number is gone, so that would mean we have 9 options left for the first digit. And hopefully that makes sense because I've used one number here, so that number is no longer available for the first choice. Usually we have 10 digits available, but since one digit has already been used from the last choice, then that means there are only 9 digits left for the first choice. Now for the second digit, 8 options are left with 2 numbers that are gone. So if I've used one number here and one number there, then those numbers are no longer available for the second digit, so that means I have 8 possible choices left for my second digit. And for my third digit, I have 7 options left because 3 numbers are gone. I've used a number here, I've used a number there, and I've used a number here. So those 3 numbers are no longer available, so that means I have 7 digits left for my third digit. So 9 times 8 times 7 times 5, that would mean I have 2,520 different outcomes. All right, let's take a look at another example here. I have a true or false exam. A true or false exam has 7 questions. If you were to guess all your answers, how many different outcomes can you have? All right, let's take a look at this. So each question has 2 options. All right, so question number 1, you could pick true or false. Question number 2, you can pick true or false. The last question, you can pick true or false. So each question has 2 options, either true or false. To find the total number of different outcomes, multiply the number of choices for each question. All right, so this is question number 1, this is question number 2, this is question number 3, and this is question number 7. So for question number 1, how many choices do you have for the first question? Well, you have 2 choices, either true or false. For the second question, you also have 2 options, true or false. And basically for the third question, you would have 2 choices as well. For the fourth question, 2 choices as well. For the 5th, 6th, and 7th, you would have 2 choices as well. So this is simply 2 to the power of 7. 2 times 2 times 2 times 2 times 2 times 2 times 2, 2 to the power of 7. And that would mean you would have 128 different outcomes. All right, let's take a look at another example where we have more choices. A multiple choice exam has 5 choices for each question. If there are 8 questions, how many different outcomes are possible? All right, so we have 8 questions and one question has 5 choices. All right, so here are my different here are my 8 questions lined up. And for the very first question, I have 5 choices. The second question, I would have 5 choices, and it's pretty gonna be 5 for every single question. So this is simply going to be 5 to the power of 8, and that's going to give you 390,625 different outcomes. All right, let's take a look at the final example here. Every license plate in BC has 3 letters followed by 3 numerical digits. If no letter or number is to be repeated, how many different license plates can be generated? Okay, so let's take a look here. So for every license plate in BC, we have 3 letters followed by 3 numerical digits. So here for the first 3 slots here, these must be letters, and for the last 3 slots, these must be numerical digits. Okay, so 3 letters followed by 3 numbers. Now there are 26 letters in the alphabet. All right, so we go from A, B, C all the way down to Z. We have 26 letters here. So for the very first choice, we can pick any letter in the alphabet. So for the very first choice, we have 26 options. Now it says no letter can be repeated. So if I've used one letter here, so for example, if I've used the letter B for my first choice, that means I can't use the letter B for my second choice. So that would mean I would have 25 choices for my second slot here. Now if I used a letter here and a letter there, that means those letters are no longer available for this last spot here. So that would mean I have 24 choices for this third slot. Alright, so that takes care of my letters. Now let's look at my numbers here. For numbers, I have 10 different numbers from 0 all the way to 9. And so for this slot right here, I can pick any number from this list. So that would mean I have 10 choices for, I guess, this fourth slot right here. Now for my fifth slot, I've used one number here. So for example, if I use the number 6 for the fourth slot, that would mean the 6 is no longer available for my fifth slot. So 6 is no longer available, so that means I have 9 choices left for this spot right here. And for my last spot, I've used a number here and I used a number there. So I can no longer use the number here and there for this slot. So that means I have 8 choices for this spot right here. So if I multiply all these numbers across, I would get a total number of 11,232,000 different license plates. Alright, so that concludes the first lesson, and we'll see you again for the next lesson.